Hi, this is Somaiah, working as assistant professor in the Department of Mechanical Engineering at Institute of Aeronautical Engineering, Hyderabad. Today, I'm going to discuss about the Bernoulli's equation, its derivation and applications of Bernoulli's equation, how it will be useful for solving different types of flows, etc. As we have did earlier, the Euler's equation, continuity equation, then the next the thing we have to discuss is the Bernoulli's equation. The Bernoulli's equation, first of all, we have to understand the statement of Bernoulli's. Also, in order to derive the Bernoulli's equation, we need certain assumptions. For that assumptions, we have to derive the particular expression, and at what condition you have to you derive the that is given by assumption. And basically, the what do you mean by a Bernoulli's equation? A Bernoulli's equation is nothing but the total energy remains constant at any section of a flowing fluid for the given assumptions. If the fluid is ideal, and if the flow is steady, and the flow will be incompressible, the flow is irrotational. So for this four characteristics, the total energy remains constant. The total energy means the pressure energy at one point, say P1 by rho g, P by rho g, and kinetic energy is V square by 2g, P by rho g, V square by 2g, and plus Z. This is nothing but total energy. The total energy will be remained as constant at a given point. So these three energies, the pressure energy, kinetic energy, and potential energy, it remains constant at any given point for the given assumption. For the assumption, if the fluid is possessing these four characteristics, viscosity should be 0. If the fluid is ideal, for ideal fluid only we can find out the 0 viscosity. Otherwise, for real fluids, always there will be viscosity. It varies based on the conditions, based on the fluid using. So, and it should be steady, where the velocity, pressure, density, and temperature remains constant from point to point. So therefore, the flowing fluid must be a steady, and if the flowing fluid is compressible, also it's not Bernoulli's we not be derived, and it won't. If it is compressible, then the derivation will be derived in different manner. But if it is compressible, that is different, and if it is incompressible, this is another case. Incompressible means where density would not change. The density remains constant. If the density remains constant, then you can call it as incompressible. So they say the same time the flow should be irrotational. The fluid particles should not rotate about their own mass centers as they are flowing. So, and for these four conditions, these three energies remains constants. Constant. P by rho g is a pressure energy for unit weight, also known as pressure head. This is also known as pressure head. Similarly, kinetic energy V square by 2g or kinetic head, also kinetic energy per unit weight or kinetic head. And similarly, potential energy is denoted by Z per unit weight, also is known as potential head. So these three energies remains constant while the fluid is flowing from a point to point for a given particular period of time. At any point, these three energies remains constant if the flowing fluid is following these four assumptions. If it possesses these four assumptions, then you can say the particular the Bernoulli's equation can be derived, and it can be applicable in such type of cases. But anyhow, in real cases, it is not possible. In real fluids, these assumptions will not be possible. We'll see the derivation of Bernoulli's equation. as we have derived the Euler's equation and continuity equation. So this is similar to the Euler's equation, the derivation of Euler's equation. And after achieving the Euler's equation, if you integrate it, then we will be achieving the Bernoulli's equation. So for deriving either Euler's equation or Bernoulli's equation, the primary thing is we have to consider a cylindrical fluid particle as it is moving over a streamline. Yes. So and its dimensions are area is dA and pressure force at inlet is PdA, and its length of the fluid particle is ds, and the pressure force acting in opposite direction at the exit of the fluid particle is P plus dou P by dou S into dA into ds. So and the vertical component due to the weight of the fluid particle is rho g dA ds, and which is acting at an angle of theta from the direction of flow. So, from the for this consideration, we will be deriving the Euler's equation and Bernoulli's equation. So these are the four forces we have discussed. These are the three forces which are acting on a fluid mass, a fluid particle. So for this, based on the Newton's second law of motion, the resultant force is which is acting on a fluid particle is equals to the mass of the fluid element into acceleration in the direction of s. So therefore, by applying the Newton's second law of motion, we will write the all resultant forces on one side, and that must be equated with the product of mass and acceleration. So these are the three forces which are acting on a fluid element. One is at inlet in the upward direction, PdA is acting. The force due to pressure is PdA minus P plus dou P by dou S into ds into dA. So this is achieved by utilizing the Taylor's series P into dA ds. So if you expand using Taylor's series at the after distance of ds from the inlet, you can get P plus dou P by dou S into ds into dA. So this is which acts in opposite direction to the flow. And another one is the force due to the self weight of the fluid particle which is acting towards down rho g dA ds cos theta. So another one is this resultant force which is acting on a fluid element. These are the three forces. One is pressure force inlet, pressure force at outlet, and weight of the element which is acting towards down, and this should be equals to product of mass and acceleration. So mass is rho into dA ds. The weight becomes rho g dA ds, but mass becomes rho into dA ds multiplied by acceleration. So along the direction s. So where in this case the as the acceleration about s can be derived. So for the following assumptions. So as acceleration is nothing but rate of change of velocity dv by dt, you can write, and v is a function of s and t. Therefore, by using chain rule of differentiation, we can achieve this expression dou v by dou s into ds by dt plus dou v by dou t into dt by dt. So from this expression, we can write v into dou v by dou s plus dou v by dou t. So here another assumption is that dou v by dou t becomes 0 as if it is a steady flow. Our assumption is that for a Bernoulli's equation, so we have to assume that the flow is steady, therefore it becomes 0. But then v dou v by dou s. So this is nothing but this expression can be substituted in the equation 1. So if you substitute in equation 1, so we'll be writing like this. So substitute as v into dou v by dou s. Then after substitution of v into dou v by dou s, if you simplify, so if you simplify, you can multiply so this product and you can cancel it. So therefore you can get a minus dou p by dou s into ds into dA minus rho g dA ds cos theta is equals to rho into dA ds. It indicates a mass, and acceleration is v dou v by dou s as we have derived earlier. So now entire equation on either side I'm going to divide with rho into dA ds. So if you divide with, we'll get minus dou p by rho into ds, rho into dou s minus g cos theta. This will be g cos theta as rho dA ds cancels. Similarly, we'll get v into dou v by dou s here. So we can rewrite this equation as dou p by rho into ds plus g cos theta plus v dou v by dou s is equals to 0. But from this diagram, we can assume that as this is theta, so between these two components, dz and ds, from this cos theta is equals to dz by ds. So if you substitute in g cos theta, the cos theta is equals to dz by ds. It can be written like this: 1 by rho into dp by ds or dp by rho. So dp by rho plus g into dz and so v into dou v. So if you multiply with the ds, substitute dz ds, then either side if you multiply with the ds, then we'll be achieving equation 3. So this particular equation 3 is known as Euler's equation of motion for a given assumptions for a fluid particle while it is moving along a streamline. So now the Bernoulli's equation is nothing but the earlier derived for the earlier derived equation. If you need a Bernoulli's equation, if you integrate the earlier derived the Euler's equation components, if you integrate those components, you will get a Bernoulli's equation. So here what we are doing is dou p by rho plus g dz and v dv. We got these three terms is equals to constant. These three energies or constant, and if you integrate it, then we'll get another equation that is known as a Bernoulli's equation. If flow is incompressible, rho is constant. So from the integration, what we will get is p by rho, integral dp by rho is p by rho, it becomes p by rho. Similarly, this becomes g into z plus this becomes v square by 2, v square by 2 n plus 1 by n, then this is equals to constant. So p by rho plus gz plus v square by 2 is equals to constant. So after dividing, then after dividing with g, then we will get this equation p by rho g and v square by 2g plus z. So if you divide with the g, acceleration due to gravity, then we will be achieving the equation 4. So that is p by rho g plus v square by 2g plus z is equals to constant. So this particular equation is known as Bernoulli's equation of motion. Bernoulli's equation of motion for a given assumption. So this equation indicates there are three different terms in this equation, also as Euler's equation. The first term indicates the pressure head, otherwise pressure energy for unit weight, and the second term is v square by 2g indicates the kinetic head, otherwise kinetic energy per unit weight, plus z, this is potential head or potential energy for unit weight. The sum of these three energies, sum of the total energy, otherwise Bernoulli statement is nothing but the sum of the total energy remains constant at any point of a flowing fluid for the assumptions are taken into the consideration. If the assumptions are not following, then the total energy may not be the same at any given points between the any given 2 points. But if the assumptions are followed, if the for particular assumptions the total energy remains constant, that is given by the statement is given by Bernoulli's. So in this, this indicates p by rho g plus v square by 2g plus z is nothing but total energy for unit weight. Energy for unit weight is equals to constant at any point of time for a flowing fluid. So if you consider, if you taken into the account of those four given assumptions. The Bernoulli's equation represents the energy possessed by a flowing fluid for unit weight of a fluid, but each fluid particle can be, each component of the equation of a Bernoulli can be defined like the pressure energy for unit weight or pressure head, this is kinetic head, and another one is potential head. Therefore, the Bernoulli's equation may be considered as an energy equation applied to a flowing fluid. This is known as energy equation. The general energy equation for the flow of fluids may be derived on the basis of the principle of conservation of energy, and is essentially a complete accounting of the work done on the fluid and the resulting change of energies of the flowing fluid. So this can be derived not only from the Euler's equation, it can be derived also from the conservation of energy, law of conservation of energy. From that also it can be derived, as the total energy remains constant. This is another approach of deriving the Bernoulli's equation. Therefore, Bernoulli's equation may also derived on the basis of principle of conservation of energy. So you can attain the same, either you can follow the principle of conservation of energy. You will get the expression for Bernoulli as P by rho g plus V square by 2g plus Z equals to constant. That means the total energy remains constant. So which is Bernoulli's equation for a steady flow. For a steady flow of incompressible non-viscous fluid in a stream tube, as derived earlier. For while a fluid particle is moving along a streamline, in such type of case, for a steady flow, for viscosity equals to 0, there should not be no viscosity. There should not be any viscosity. That means that it should be ideal fluid. If for ideal fluid only it is possible. In case of ideal fluid, viscosity remains 0. Because as assumption of Bernoulli's, before deriving the Bernoulli's equation only the assumptions are provided. It must be a steady, must be incompressible, irrotational, also non-viscous. Ideal, it should be ideal. Ideal means non-viscous. So for that cases, this equation 4 is applicable. However, for the steady flow of an incompressible real fluid, if the real fluid is existing, because we have all real fluids for study, we don't have the ideal fluid. So in such cases, there must be a loss. Always there must be a loss between the two sections, because it is in real case there must be always the friction will be there, and due to friction, due to viscosity, due to compressibility, and all due to all these parameters, there will be a loss. The loss is given by loss of head, HL. HL denotes the loss between the 2 points, section 112 to section 22. In such cases, the same equation can be written as actually the Bernoulli's equation is P by rho g V square by 2g plus Z equals to constant. But between 2 points, there are losses also existing as it is real. So as there is a loss, so in this case we have to adapt the total energy at 2 different points. So that is that it can be written as P1 by rho g plus V1 square by 2g plus Z1 is equals to total energy at point 2. Total energy at point 1 is equals to total energy at point 2 plus losses HL. So the loss of head due to so many parameters. Majorly, the loss of head due to friction will be taken as a major energy loss. Loss of head due to another reasons may be considered as a minor energy losses, and that will be total energy loss is given as HL. It states in steady flow of real fluid, the total head for Newton or for kgf of flowing fluid at any section is equal to that of any subsequent section plus loss of head. So the loss of head will be added as it is a real fluid. So in this case, the two sections in flowing fluid are lying at the same height above assumed datum, then Z1 is equals to Z2. As the datum is the same, you can eliminate the Z component, potential component. If the study of a particular flowing fluid is in vertical direction, then Z1, Z2 will differ. As if it is inclined also, it will differ. If it is horizontal, if the datum is horizontal from the flowing fluid, then it can be equal, Z1, Z2 equal. So if you eliminate the Z1, Z2 from the previous equation, from this equation, if you eliminate Z1, Z2 as the datum is constant, The remaining Bernoulli's equation can be written like this: P1 by rho G plus V1 square by 2G equals to P2 by rho G plus V2 square by 2G plus HL, which gives the pressure velocity relationship. There is a from this relationship you can determine the unknown pressures or unknown velocities. Also, if the loss is given, as it is a real fluid, loss will be provided. Otherwise, you can calculate the losses. So you can, from this Bernoulli's equation, between two sections, we can determine unknown pressures or unknown velocities. So this expression from Bernoulli's expression, you can get a relationship between pressure and velocity. These include the problems of gas flow and the flow of liquid in horizontal pipes. If the energy loss between two sections can be neglected, then the previous equation becomes like this: P1 by rho G plus V1 square by 2G equals to P2 by rho G plus V2 square by 2G, as HL is eliminated. So it is indicated from the above equation that if the flow passage is such that V2, the velocity of flow at section 2 is greater than V1, the velocity of flow at section 1, then P1, the pressure at section 1 will be greater than to the P2, the pressure at section 2. So then the equation will be satisfied. So from this in actual practice also, it is observed that if any section of flow passage, due to the considerations of continuity, the velocity of flow increases, then the pressure at this section reduces, and vice versa. So the pressure and velocity relationship based on the curvature, otherwise through which surface it is flowing, based on that it can be varied. As if it is flowing through a convergent passage, then as here in this case the fluid particles will starts converging, therefore where velocity increases but pressure decreases. So therefore, as the velocity increasing, as the velocity decreasing, then pressure increases. So these are vice versa, they will be changing. Bernoulli's equation finds wide applications in the solution of many fluid flow problems. In fluid flow problems, especially in order to solve by considering these four cases, and if the four cases are deviating because we don't have ideal fluid, therefore for real fluid, and it may be steady or unsteady, it may be compressible or incompressible. Based on that, it can be applied in various problems. It can be applied. So in case of as a part of Bernoulli's equation and its applications, we have the number of devices for which we will be deriving the discharge equations, and the rate of flow will be calculated. So in these devices we can apply the Bernoulli's equation. So as part of applications of Bernoulli's equation, the first the device which we are going to consider is venturimeter. The venturimeter through which we'll measure the rate of flow. So it's a measuring device through which we'll measure the rate of flow which is flowing through a pipe, and it was explained otherwise invented by venturimeter by G.B. Venturi, Italian physicist in 1797. It is invented by G.B. Venturi. The basic principle on which venturimeter works is, so by creating the cross-sectional area, by varying the cross-sectional area, and the pressure difference will be created. The pressure difference will be utilized for the measurement of the rate of flow. If the fluid is flowing through this pipe, uniform pipe, so here we cannot adapt the principle of venturimeter. But here, if you reduce the cross-sectional area, then there will be a difference in pressure. So this the here pressure will be high, here pressure will be high, here pressure will be less. So this pressure difference will be measured, and it will be utilized for the calculation of rate of flow through this venturimeter. So in this diagram you can see, first this is uniform pipe through which the water is flowing, liquid is flowing, and afterwards it gradually starts converging, and it flows through a throat, then gradually converging. So thereby there are two pressure taps here before the liquid entering into the venturimeter. there is one pressure tap. It reads P1. This is a high pressure if you compare with the pressure at section 2. At throughout here velocity is increasing, but pressure will be decreasing. So due to this, there will be a pressure difference between these 2 points. So this pressure the pressure difference will be utilized for the measurement of the rate of flow through a particular pipe. Rate of flow can be calculated by utilizing the pressure difference between these 2 points. So the rate of flow, in order to measure the rate of flow, Q equals to CD A1 A2 to root 2GH by root of A1 square minus A2 squared. In order to derive this equation, we will apply the Bernoulli's equation on section 1 and section 2. At these two sections, the Bernoulli's equation will be applied. So the Bernoulli's equation will be applied, the statement also, we have gone through the statement and its assumptions. So at 2 different points, the total energy remains constant. And if it is a real fluid, there will be a loss of head. So that will be total energy at one point is equals to total energy at point 2 plus loss of head. So that we will apply between these two sections. Therefore we will be achieving this expression. So that will be useful for measuring the rate of flow which is flowing through a pipe. So this is the application of a Bernoulli's equation, one of the application of Bernoulli's equation. Similarly, orifice meter. The orifice meter also the same working principle on which the venturi meter works. Here also the pressure difference will be created, and the pressure difference will be utilized for the measurement of discharge through orifice meter. So through here also the discharge expression will be same, but here we have to consider A1 and A0. These are the two areas. So this is a A0. So yeah, before entering into orifice, the pressure will be high. Once after flowing through this orifice, through this small slit, then the velocity will be increasing at this point, but the pressure will be decreased. So due to this pressure difference, we are measuring this pressure difference and utilizing for measurement of discharge through a venturi meter. So to measure the rate of flow through the venturi meter, we need a expression for that. For deriving the particular expression, we need the Bernoulli's equation. The Bernoulli's equation, what it is going to do is, it is going to be applied on these two sections. At these two sections, it will be applied, and we will be deriving the rate of flow expression. Similarly, nozzle meter or flow nozzle. The flow nozzle or nozzle meter is also one of the device used for measuring the discharge through the pipe. So the difference between nozzle meter and venturi meter is, here the convergent will be there through which, like orifice, so there will be a small slit will be there, but here like a venturi, small gradual conversion section is there. So there will be a emitting of divergent cone and throat. So this is nothing but a nozzle flow meter. Through this also there will be rate of flow measurement. So if you need a rate of flow which is flowing through a particular pipe, you can adapt venturi meter or orifice meter or flow meter, the flow nozzle. So in order to measure the flow rate, we have to apply the Bernoulli's equation at two different sections, and derive the expression for a rate of flow through that particular device. So therefore we are applying the Bernoulli's statement, Bernoulli's equation, in order to measure the rate of flow through a particular pipe. So another one is in pitot tube also. The pitot tube is used for measuring the velocity of flow. In order to measure the velocity of flow, the expression can be derived by applying the Bernoulli's equation. So at these 2 points, Bernoulli's equation can be applied at these 2 points. So by applying the Bernoulli's equation, we can calculate we can derive, and later on we can calculate the velocity which is flowing through a pipe, or which is flowing through a particular point in a stream. These are the references. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.